I think it's fair to say that the question, what if an asteroid hit the Earth, begins as a shiver and ends as a lesson in perspective. The night sky looks still and eternal, but it is alive with small wandering worlds. Shards from the making of the planets, snow-dark comets on long ellipses, and a diaspora of rubble that occasionally wanders a little too close to home. When you first hold that idea in mind, it can feel stark, even unsettling. But I've always found that when you look carefully, when you replace fear with curiosity, the cosmos reveals not only its dangers, but also the growing competence of a species that has learned to read the sky and, increasingly, to shape its own fate. Let me begin with scale, because scale is the quiet architect of our emotions. Most space rocks that meet our atmosphere are no bigger than a suitcase. They flare, they sigh into vapor, and a puff of meteoric dust drifts down like the memory of a snowstorm. But every so often, a body a few tens of meters across arrives fast and oblique. It does not survive the air, it explodes within it. Over southern Russia, in the city of Chelyabinsk, that is precisely what happened in the middle of February of the year 2013. A stony object, roughly the size of a modest house, disintegrated high in the atmosphere, releasing energy comparable to several 100,000 tons of chemical explosive. Windows burst. People were injured by flying glass. The sky roared like a train passing through the clouds. The planet was unmarked. The people were not. It was a reminder that even small cosmic stones can be loud when they meet air at dozens of kilometers per second. Now step up a rung on the ladder of size to the objects one might call city killers, hundreds of meters across. These are the ones that keep survey astronomers awake, not out of dread, but obligation. There is a very practical reason for that. A rock around 140 meters across carries enough kinetic energy to devastate a metropolitan area, yet it is still small enough to be missed if you only stare at the sky with modest telescopes and intermittent attention. This is why the United States' Planetary Defense Coordination Office, those are the people whose job it is to think about this, methodically exists to find, track, and if necessary, help us plan to nudge such objects away. Their mandate is simple to say and difficult to do. Discover the vast majority of near-Earth objects large enough to matter. Work with partners around the world to assess the risk and develop the means to act. Act. It's an evocative word. For most of human history, acting on a celestial threat meant prayer and story. In the 21st century, it means engineering. In late September of the year 2022, a small spacecraft was dispatched to deliberately collide with a small moonlet called Dimorphos, which orbits a larger asteroid named Didymos. The mission had a deceptively gentle name, the Double Asteroid Redirection Test, but what it did was profound. It changed the period of Dimorphos's orbit by a measurable amount, minutes rather than seconds, which in mechanics is the difference between a nudge and nothing at all. For the first time, humanity altered the motion of a celestial body in a controlled experiment designed to test a method of planetary defense. The numbers matter, because physics is a book written in numbers, the orbital period shortened by a little over half an hour. That figure is not a guess. It's the signature of momentum transfer written in starlight and radar echoes. And because science is a conversation rather than a shout, our colleagues in Europe launched a follow-up mission. It's called Hera, and it slipped away from Florida in early October of the year 2024, bound for a rendezvous with the binary asteroid in the latter half of the decade, where DART, let me say the full name again, the Double Asteroid Redirection Test was an experiment in imparting a shove. Hera is an experiment in understanding the consequences of that shove. What is Dimorphos made of? How did its shape and internal structure respond? How big is the crater, if any? These are not academic curiosities, they are the knobs and dials of future missions. If you want to nudge a rock safely, you must know what sort of rock it is. Of course, there is a more famous stone. 66 million years ago, in what is now the Yucatan Peninsula, a body many kilometers across struck the Earth and excavated a crater nearly 200 kilometers wide. The name Chicxulub has become almost a character in our deep time mythology, the harbinger of the end of the non-avian dinosaurs, and much else besides. We no longer think of that event in vague terms. We can point to the ring of cenotes that trace the buried rim. We can drill into the shattered rocks. We can weigh the energy and trace the waves that raced around the ocean basins. This was not a local disaster, it was a global one, the environment itself bending under the force of a blow. The lesson is not that such things are common, the lesson is that they are possible, and the stratigraphy of our planet remembers them. Between the house-sized visitor that pops windows and the continent-sized violence of Chicxulub lies the broad middle ground where planetary defense truly lives: detection and time. If you know where the rocks are, and you know early enough, almost everything else becomes easier. This is why a new generation of observatories matters. In Chile, the Vera Rubin Observatory has begun to open its eyes. Its survey is designed to sweep the southern sky again and again, noticing what is new, what has moved, what has changed. Variable stars, supernovae, the flickering hearts of galaxies, yes, but also the asteroids that drift silently between the planets. By the middle of the decade, Rubin revealed its first images, and as the survey matures, it will not just take pictures of the sky, it will take pictures of the sky changing, and that is precisely what you want when you are searching for moving points of light. Space-based eyes will join the watch. A dedicated infrared telescope called the Near-Earth Object Surveyor. Let me translate that for narration. The NEO Surveyor has been contracted for launch no earlier than late in the year 2027. Infrared matters because dark rocks that reflect poorly in visible light still glow with heat. From space, above weather and atmospheric haze, such a telescope can scan for warm, moving dots that ground-based telescopes might miss. The goal is not merely a catalogue. The goal is a margin, years or decades of warning for anything large enough to be seriously dangerous. Because time turns an impact into a navigation problem, and navigation problems are precisely the kind we know how to solve. There is as well a celestial appointment that will focus the world's attention on small worlds and their orbits. In mid-April of the year 2029, an object named Apophis will pass closer than many satellites, yet safely by. It will be visible to the naked eye across parts of our planet, and it will not hit us. But it will give us a front row seat to the subtle dance between gravity, spin, and rubble, and a repurposed spacecraft now called OSIRISAPEX will fly with it, watching how Earth's pull resculpts a small world. Think about that. We will study in real time how a planet's gravity can rearrange an asteroid. That's science as rehearsal, and rehearsal is precisely what you want before opening night. So the stage is set. We know what the small ones can do. We remember what the large one once did, and we are building the means to see, and if necessary, to steer. In the next part, I'd like to move from the wide canvas, surveys and statistics, into the specifics of consequences. What actually happens if a stony asteroid of different sizes arrives over land or sea? How air turns from shield to hammer, how shockwaves, thermal radiation, and tsunamis unfold, and why the details of angle, speed, and composition are the difference between a loud day and a bad era, and from there to how, in practice, we would nudge a rock ever so slightly so that it misses us by a comfortable astronomical mile. I promised we'd move from the wide canvas to the texture of consequences, because what happens in the air over land or at sea is decided by a handful of variables that sound simple: size, speed, angle, and composition, but combine into a symphony. The first thing to grasp is that our atmosphere is not an empty hallway. It is a fluid, and a fast-moving rock feels that fluid as pressure, ram pressure, that grows with the square of the speed until the stone fails. That is why many small asteroids do not make craters at all. They fragment, they dump their energy into the air, and the air, suddenly hot and roaring, becomes the hammer. The Chelyabinsk event is our modern tutorial in that physics. A stony body on the order of a large room in size arrived at many kilometers per second, began to shed material, then catastrophically broke high above the ground. The blast wave raced outward, and windows became shrapnel. It is a gently chilling lesson. You do not need a crater to have an impact. The air itself can carry the blow when a fragile visitor fails aloft, as detailed in the field studies and reconstructions that followed. Scale that up to the realm of the so-called city killer, an object a few hundred meters across, and the vocabulary expands. You may still have an airburst if the body is weak, but you are now well into the regime where the ground may be involved. If a stony projectile remains coherent long enough, it can reach the surface and excavate a crater. If it does not, the airburst can nevertheless flatten structures across many kilometers. The historical analogue often invoked is Tunguska, a remote Siberian catastrophe in the early 20th century, in which a probable stony visitor exploded above the taiga. No crater was found, and yet millions of trees were toppled across an area almost the size of a small country. That event is a reminder that an aerial detonation can do ground damage on a continental scale when the energy release is measured in megatons rather than kilotons. Composition is the personality of the projectile. Iron-rich bodies are tough. They tend to punch deeper into the atmosphere. Smaller ones can reach the ground and dig neat, bowl-shaped craters, even when their diameters are only tens of meters. In Arizona, you can stand on the rim of such a scar, Barringer Crater, sometimes just called Meteor Crater, and look across a kilometer-scale bowl excavated by an iron mass roughly the size of a small house. It is an object lesson in how a compact metallic body couples energy to the ground with ruthless efficiency, no airburst required. Speed and angle set the choreography. Typical entry speeds for asteroids are in the high teens of kilometers per second. Short-period comets are faster still, and the rare long-period visitors can be faster again. The most probable impact angle is neither grazing nor vertical, but somewhere around mid-inclination, where coupling into the atmosphere and ground can be particularly effective. There is a striking case study from deep time, the Chicxulub impact, which closed the Great Mesozoic chapter. Modern modeling and geophysical sleuthing suggest a steeply inclined strike, something like 45 to 60 degrees to the horizontal, which maximized the lofting of dust and sulfur into the high atmosphere and, with grim efficiency, worsened the climate consequences. Over the sea, the story becomes subtle in a way that is easy to miss if one imagines cinematic waves racing across entire oceans. The physics of water is not the physics of air, and the coupling of impact energy into long-range ocean waves is surprisingly inefficient for the common sub-kilometer cases we worry about this century. Modern workshops that brought together impact modelers and tsunami experts reached a broad consensus. For the sizes we are most likely to see, severe flood damage tends to be a near-field coastal hazard, especially on shelves and in bays, while far-field ocean-spanning tsunamis are unlikely from small and moderate impacts. Airbursts over water, so common for stony bodies, are even less efficient at making large, deep ocean waves. That doesn't make the nearshore problem trivial. It means we must plan for it with clear eyes, rather than with myths. And because the atmosphere is our mediator, there is a quiet rule of thumb. For small visitors housed to building scale, the air is a shield. For modest visitors, field to stadium scale, the air can become a club. And for large visitors' hills on ballistic arcs, the air is irrelevant theatre. Once you cross into the realm of the multi-hundred-meter asteroid, composition and angle decide whether you have a crater and how big. Planetary scientists have encoded these relationships into scaling laws that link the incoming mass and speed to the size of the transient cavity in rock, and thence to the familiar, larger rim-to-rim crater you can walk around. Those laws are not abstractions. They are informed by field geology on Earth and other worlds, and they allow us to translate a moving dot of light in the sky into consequences on the ground with useful fidelity. Where then does the threshold for truly global mischief sit? Here we can be comfortingly specific. The large, civilization-wide risks are associated with objects roughly a kilometer across or larger rare beasts in today's catalogue. We have identified the great majority of those, and none threatens us on relevant timescales. The tier below, objects larger than roughly 140 meters, can cause regional devastation, and there are many more of them. Finding and tracking this population is a work in progress, and it is precisely where new surveys on the ground and in space are aimed. This is not hand-waving optimism. It is a portfolio of practical goals, dates, and instruments. All of this detail matters because it tells us what to do if one day the ephemeris says we have a visitor on an uncomfortably precise appointment. The tactics depend on time. Years or decades of warning transform a potential impact into a navigation exercise, and navigation is a game we have learned to win. A nudge delivered far away translates into a comfortable miss at Earth. The methods range from the elegantly simple to the beautifully patient. Kinetic impactors that kiss the asteroid off its path by momentum transfer, gravity tractors that hover and whisper with steady tug, and, held in reserve for late notice, or very large bodies, energetic standoff options that couple impulse without fragmenting a rubble pile into a cloud of trouble. We will talk through those options one by one, because the engineering details are poetic in their own way. How you paint a rock brighter to exploit sunlight, how you arrive at just the right angle and speed to maximize a nudge, how you characterize a spinning pile of gravel before you dare to touch it. Before we go there, I want to close this chapter with a small, humane point that I think is worth saying aloud. We are often tempted to equate cosmic danger with cosmic indifference. But the real story, written in observatories and mission control rooms, is that the universe presents the challenge and we bring the care. The more precisely we understand airburst physics, crater scaling, ocean wave coupling, and the statistics of sizes and angles, the more modest the risk becomes, because knowledge stretches the timeline and widens our menu of gentle interventions. And that, to me, is the most reassuring truth. In the next part, let's open that menu and linger over each method, how a kinetic impactor actually works, what we learn from the Dimorphos experiment about momentum transfer and ejector plumes, how a gravity tractor holds station and whispers over years, and why detection, characterization, and international coordination are the quiet foundations beneath any brave maneuver we might one day need to fly. Let's open the menu of gentle interventions, beginning with the one we have already flown. A kinetic impactor is, in essence, a precise nudge delivered at cosmic speed. In late September of the year 2022, the Double Asteroid Redirection Test, let me say the full name so it is clear-struck, the small moon Dimorphos that orbits the larger asteroid Didymos. The measurable result was beautifully unambiguous. The orbital period of Dimorphos shortened by roughly 33 minutes. That is not a model. That is a measurement derived from light curves and radar, written into the timing of mutual eclipses and echoes. The physics beneath that change contains a subtle grace note. The plume of ejector acted like a rocket exhaust, amplifying the shove beyond the simple momentum of the impactor itself. In other words, you do not just push the asteroid, you also kick off debris that pushes back. If you watch the imagery from the small Italian companion spacecraft, its name was Lycia Cube, the light Italian CubeSat for imaging of asteroids. You will remember the flower of dust that opened in the minutes after the strike. Telescopes on Earth, and later careful reconstructions, traced that cone of material as it evolved, brightening the system dramatically before it settled. That expanding blossom is not merely cinematic, it is the signature of momentum enhancement, the very thing we hope to measure so that future deflection designs can be sized with confidence rather than with guesswork. The European Space Agency's follow-up mission, named Hera, is the second act of the same experiment. Hera launched successfully in early October of the year 2024 and is cruising toward the Didymos system for arrival in the latter half of the decade. Once there, it will release two small companion craft, Juventas and Milani, to help map the mass, the shape, the internal structure, and the impact site in exquisite detail. If you want to design a future nudge, you need to know whether your target is a monolith or a rubble pile, how it spins, whether it rings like a bell or sighs like a sand dune. Hera's task is to turn that poetry into numbers. There is a practical art to kinetic nudging. The change you need in the asteroid's path is remarkably small, often millimeters per second in velocity, provided you have years of notice, so that tiny alterations accumulate into a miss by a comfortable astronomical margin. But those millimeters per second are delivered most efficiently when you know your target. A fast spin can tilt the plume and steal some of your push. A weak, porous surface can soak up energy, or, conversely, yield vast sprays of ejecta that amplify it. That is why we care about the details of the dimorphous plume, the shape change, and the way the binary's orbit settled after the collision. They are the first hard-won data points on how a real asteroid responds in nature, not just in simulations. Sometimes, though, the elegant shove is not the right tool, especially if the warning is short or the object is large. In that case, we turn to a concept that is as patient as it is precise: the gravity tractor. The idea, first set down clearly by Edward Lu and Stanley Love, is to use a spacecraft's own mass and thrusters to hover near a threatening body and let gravity do the work. The spacecraft does not touch the asteroid, it simply loiters just off to the side, firing its engines outward, so exhaust never strikes the surface. Over months to years, the mutual attraction between spacecraft and asteroid acts like a gentle tow line, tugging the rock onto a safer path. The beauty of the gravity tractor is its indifference to the asteroid's quirks. Rubble pile or iron monolith, tumbling or serene, it does not matter very much, because you never kick up dust or bounce off boulders. The price you pay is time. It is a method for the early warning era. Held in reserve is the option nobody reaches for lightly: a nuclear standoff deflection. The phrase standoff is important. You do not want to pulverize a fragile asteroid into a swarm of problems. You want to ablate its surface at a distance, bathing one hemisphere in a burst of radiation so that material flashes off and, like an exhaust, imparts a decisive impulse. The physics says it is effective for large bodies and short timelines. The policy says such an action demands international consensus, transparency, and rehearsal in law, as well as in engineering. Over the last decade, technical reviews and policy studies have converged on a sober view. Kinetic impactors and standoff nuclear devices are the most mature, impulsive options, with the gravity tractor and related slow push methods as complementary tools when time allows. It is not bravado, it is a menu ranked by urgency and consequence. All of these maneuvers rely on a foundation that is quieter than a launch, but just as vital: characterization. You cannot nudge what you do not know. Thermal infrared surveys from space, most notably the mission called Near Earth Object Surveyor, are designed to find the darker, warmer rocks that visible light searches can miss, and to estimate their sizes rather than just their brightness. On the ground, planetary radar acts like a cosmic tape measure and camera combined, collapsing orbital uncertainties and sketching shapes and spin states at astonishing fidelity. The long-serving Goldstone system, part of the Deep Space Network in California, routinely sharpens orbits and reveals whether a newly found dot of light is a peanut-shaped monolith, a binary, or a slow tumbling shard. Each of those details feeds directly into how you would deflect it. There is also rehearsal in the sky itself. In April of the year 2029, the asteroid Apophis will pass within geostationary distance, a safe but intimate encounter. NASA has retargeted the spacecraft that returned samples from the asteroid Bennu. It now bears the name OSIRISAPEX. The origins, spectral interpretation, resource identification, and security Apophis Explorer. It will slip into proximity operations around Apophis shortly after the close pass and watch how Earth's gravity changes a small world, its spin, its surface, perhaps even its interior. I like to think of that encounter as a live fire drill in celestial mechanics. It is not a threat. It is a masterclass in how orbits and rubble respond when a planet leans in. And above the engineers and scientists sits an international architecture that quietly links the observatories, the mission planners, and the decision makers. The International Asteroid Warning Network, those words are important because they describe the task rather than the flag shares discoveries, refines orbits, and issues notifications. The Space Mission Planning Advisory Group brings space agencies together to think about how, in practice, a deflection campaign would be flown. Both were encouraged by the United Nations through its Committee on the Peaceful Uses of Outer Space, and their status has been reaffirmed in recent years with regular reports, exercises, and updates. In truth, planetary defense is a profoundly international enterprise. Rocks do not carry passports, and neither should our response. So, the toolkit is on the bench: measured shoves, patient toes, last resort standoffs, all resting on better eyes and better understanding. In the next part, I want to bring that toolkit down to Earth, quite literally, by asking how warning becomes planning. What does a risk scale really mean for a mayor or a coastal community? How do radar updates change evacuation windows for an airburst over water versus over land? How do exercises from the International Asteroid Warning Network to civil protection agencies turn celestial mechanics into timetables and calm instructions? Let's walk through a day when the dot of light is real, the probability is uncomfortable, and the months ahead are a choreography of measurements, decisions, and quietly reassurance. So this is where warning becomes planning. When a moving point of light appears on the risk lists, the first thing I want is a clear, shared language for how worried should we be. That's what the Torino scale gives us, a simple integer ladder from 0 to 10 that translates orbital calculations into plain English categories for decision makers and the public. 0 is routine, the background murmur of harmless flybys. A value of 1 means worth watching. By the time you climb to the middle of the scale, you're talking about events that warrant coordinated preparation. It was adopted by the International Astronomical Union a quarter of a century ago, and it remains the dashboard dial we glance at first. Under the bonnet, professionals use a second gauge, the Palermo technical scale. It's logarithmic and deliberately technical, combining the probability of impact with the expected energy, and comparing that risk now to the background risk of random impacts between now and the nominal date. A Palermo value below 0 generally signals less than background, while positive values climb as a potential impact grows both more likely and more energetic. It's a quiet but powerful way to prioritize attention and telescope time long before a mayor needs to brief a city. Those dials are fed by an automated sentinel that never sleeps. At the Jet Propulsion Laboratory, the Center for Near-Earth Object Studies runs Sentry software that continuously ingests new astrometry, propagates orbits forward for more than a century, and flags any set of observations compatible with Earth impact on any date. Late in the year 2021, NASA brought a new version online, Sentry 2, that replaced the older line of variations method with an extended filter that can natively handle awkward cases and subtle physics like the Yarkovsky effect, the tiny thermal push that can drift an asteroid over decades. That might sound esoteric, but in practice it means fewer false alarms, quicker convergence, and better use of precious follow-up time on big telescopes and radar dishes. When a solution crosses the threshold from interesting to actionable, the international plumbing matters as much as the mathematics. The International Asteroid Warning Network, encouraged by the United Nations, serves as the clearinghouse for discovery notes, orbit updates, and, crucially, for consistent public notifications. It is paired with the Space Mission Planning Advisory Group, which gathers space agencies to think through what mission you would actually fly if a deflection were needed. That architecture is not decorative. It is the route by which a discovery in Chile or Hawaii becomes a brief on a minister's desk in Rome or Tokyo with the same numbers and the same tone. Because rehearsals make calm possible, we practice. In April of the year 2024, NASA's Planetary Defense Coordination Office and the United States Federal Emergency Management Agency convened the 5th Interagency Tabletop Exercise, this time with the Department of State assisting. The scenario was fictional, the conversations were not. Over 2 days, participants walked through the cadence from first detection to impact probability updates, international notifications, and the difficult choices a government must weigh if a launch window for a kinetic nudge is tight. The public summary exists for a reason. Transparency is part of preparedness. Those exercises sit alongside national strategies whose timelines extend beyond a news cycle. In 2018, the United States published its first Near-Earth Object Preparedness Strategy and Action Plan, laying out detection, assessment, deflection, and emergency response roles. In April of 2023, that plan was updated and sharpened. It noted soberly that less than half of the objects capable of regional devastation had yet been catalogued, and that improved survey capabilities are essential not as an abstraction, but as a way to turn years of lead time into a navigation problem rather than a disaster response problem. That is the essence of planetary defense: generosity with time. Let me make this tangible with a day-in-the-life sketch. Imagine a newly discovered object shows up on the Sentry risk table with a Torino value of 1. The probability is tiny. The time horizon is, say, a few decades. IAWN issues a short technical note inviting follow-up observations. As new astrometry arrives and radar paints the object's shape and spin, the uncertainty ellipse collapses. Perhaps the probability falls to effectively 0. That is the most common outcome. If, instead, the probability inches upward, Palermo creeps towards 0 and beyond, and the scenario becomes one of prudent preparation. The same plumbing that shares ephemerides starts to share draft communication lines and consequence modeling with civil authorities. The goal is not to frighten, it is to coordinate. Communication is not an afterthought, it is a discipline. Emergency managers are trained to issue clear, tiered alerts with unambiguous calls to action, and they do not want astrophysicists freelancing in that space. So part of the preparedness playbook is simply aligning our language with theirs, warning levels that map cleanly onto protective behaviors, messages that evolve as confidence evolves, and a bias toward practical detail over cosmic drama. The guidance is generic by design. Templates for alerts and warnings exist, so you are not inventing them on the day you need them. Now, suppose the best solution is not a launch, but local protection from an airburst, an outcome we know can happen because stony bodies often fail in the air. Here, the physics translates into surprisingly specific planning advice. In earlier studies and exercises, impact effects modelers advise that, if the risk is an aerial detonation over land, evacuation laterally, out of the projected damage footprint, can be safer and faster than trying to outrun a forward shock. That you stage medical resources for lacerations and blast injuries, and that you emphasize move away from windows messaging because flying glass is a dominant hazard. None of that is cinematic. All of it is humane. If instead, the threat footprint is coastal, say a low probability impactor whose best fit path grazes a continental shelf, then the conversation shifts to near-field surge and inundation in bays and harbors. Here, the emergency management world leans on the same tsunami playbooks it uses for earthquakes, with one twist: the timescale and confidence improve with each radar pass and each night of astrometry. In that sense, space science and civil protection share a metronome. We both want frequent, reliable updates that turn maybe into move. The Planetary Defense Conference scenarios you sometimes see reported in the press are designed to drill exactly that handoff. Threaded through all of this is humility about uncertainty. Our monitoring has improved. Sentry 2 can account for tiny, non-gravitational drifts that once demanded artisanal handling, but unknown unknowns shrink only with observation. That is why new survey telescopes, thermal infrared missions, and planetary radar are not luxuries. They are how you buy time. And time is the currency that turns a handful of millimeters per second in velocity change, delivered years in advance, into a comfortable miss by an astronomical mile. In the next part, I'd like to walk the other pathway when prudent preparation tips into mission mode. What does the calendar look like if a kinetic nudge is on the table? How do you size the shove from the first light curve and radar echoes? Who decides when to launch, when to stand down, and how to communicate the long, quiet months while a small spacecraft lines itself up thousands of kilometers away to arrive as a whisper that moves a mountain of rock by the thickness of a hair and yet moves our odds by everything that matters? Right, let's imagine the day the dial nudges from prudent preparation to mission mode. The mood in the room changes, not because panic is useful, it never is, but because calendars suddenly matter. In my experience, there is a beautiful clarity when physics meets a deadline. You begin by turning a probability cloud into a trajectory that can be acted upon. That means more astrometry, more radar, more patience. With each night of data, the uncertainty ellipse tightens, and the target point where a tiny nudge yields a safe miss drifts into focus. The aim is not to shove the asteroid heroically at the last moment. The aim is to adjust its arrival at what orbital dynamicists call the target plane by a few kilometers, months, or years in advance, so the rock passes harmlessly ahead of or behind Earth by a distance that would feel absurdly vast if you were standing on a runway, but is, in celestial terms, a hair's breadth we can engineer. From that refined ephemeris, the mission calendar writes itself in pencil first, pen later. There is the spacecraft you can build in time, the launch window the planets allow, the cruise trajectory that threads gravitational waypoints with elegant thrift, and the geometry at arrival that maximizes the effectiveness of your nudge. Much of this is quietly unromantic. Can your solar arrays deliver enough power at the distance you must fly? Can your propulsion deliver the necessary delta V, let me say that as change in velocity, without compromising the mass you need for a meaningful impact? The navigation team begins plotting optical navigation campaigns. The communications team books time on the big dishes, and the flight dynamics team starts talking in the language of approach cones, phase angles, and the B-plane, the mathematical screen on which a miss becomes a number everyone can see. Sizing the shove is where the poetry of numbers returns. You begin with the desired missed distance at Earth and work backwards along the orbit to ask how many millimeters per second of velocity change delivered at which epoch will integrate into that safe passage. The earlier the nudge, the smaller the push. Momentum transfer is your currency. The asteroid's mass and the spacecraft's closing speed form the principal, while the behavior of the surface, the ejector plume, determines your interest rate. If you suspect a rubble pile, you carry a margin, because the plume can either gift you a momentum bonus or swallow your effort in a sigh of dust. If the body is iron-rich, compact, and cohesive, you can be more confident that an impact at a precisely chosen angle will couple cleanly. Decision-making is, by necessity, layered. The scientific community proposes mission designs and quantifies confidence. Space agencies evaluate feasibility against the clock and the budget. Elected leaders weigh the societal risk of doing nothing against the cost and consequence of doing something. It sounds ponderous, but it is remarkably grounded. The more precise our orbits, the cleaner our consequence modeling, the calmer those conversations become. Somewhere in the middle of that architecture sits a go-no-go date tied to the last launch opportunity that still leaves time for a course-correcting nudge to accumulate. If you have ever watched a countdown, you will know that go-no-go is not a dramatic flourish. It is a discipline that keeps complex systems honest. Then comes the choreography of building a small machine that must behave impeccably very far from home. The structure is sized to survive launch loads, yet be as light as honesty allows. The guidance, navigation, and control system is tested against digital asteroids that tumble and glint as the real ones do. Cameras are trained to find faint, moving points against a starfield and to keep those points precisely centered while thrusters whisper. Fault management is written with a kind of generous paranoia. If a sensor saturates, do this. If a star tracker dazzles, do that. If a valve sticks, take the safe branch. I have always admired this part of spaceflight. It is where humility and confidence meet the humility to expect the unexpected, and the confidence to write it down in logic the spacecraft will obey when we are asleep. Public communication does not pause while aluminium is machined. If anything, it becomes more important. There is a public to brief local authorities to keep aligned with the reality of changing probabilities, and a hazard communication community to ensure that our language maps cleanly onto protective actions should the mission suffer a setback. Clarity is kind. We are launching because early action is easy, we have margins baked in, here is what we expect to learn, even if the risk declines as often happens. That sort of tone matters. It prepares people to be relieved, not embarrassed, if a risk evaporates under the light of better data. In planetary defense, a cancellation can be a victory. It means we bought time for understanding. Launch day, when it arrives, is almost ordinary by design. Ordinary is good. The rocket flies, the spacecraft separates. The first call home comes through a deep space antenna with the comforting banality engineers adore. Systems are nominal. Cruise can be long and quiet, punctuated by trajectory correction maneuvers so slight you could miss them if you blinked at the telemetry. Navigation teams practice their approach campaign on archived starfields. Principals rehearse press briefings. Sim rooms run what-ifs until the improbable has lost its capacity to surprise. Meanwhile, telescopes on Earth continue to track the asteroid. If the probability of impact shrinks to zero, as it often will with improved data, you do not waste a mission. You pivot to reconnaissance, to science, to rehearsal for the next time. That is not hedging, it is the ethic of stewardship. As the encounter nears, autonomy gradually takes the lead. Light takes minutes to cross the gulf, so the spacecraft must recognize the target, reject imposters, refine its aim, and make micro-adjustments without waiting for us. The last day becomes a kind of slow-motion exhale. Images sharpen, the body's rotation reveals boulders and shadows, and the navigation cameras begin to solve a problem as old as archery: hit the right place at the right angle. The target is chosen to maximize momentum transfer and minimize uncertainty, often downrange of the center of mass, often on a sunlit, well-characterized patch where small-scale topography will not surprise you. At the end, the final thruster pulse is issued. The vehicle locks its attitude, and the signal steadies into a tight beam that will wink out at the moment of contact. A few minutes later, observatories on Earth and in space see the system flare as dust rises. Sometimes there is no visible drama at all, just a change written into the timing of shadows and echoes in the days that follow. That quietness is part of the beauty. Physics does not need fireworks to have done its work. And then, perhaps the most human phase, verification. Did we deliver the change in orbital period we designed? Did the plume amplify the shove by the factor we hoped? Are there secondary effects, spin state changes, shape changes that matter for future designs? This is where reconnaissance craft, ground-based radar, and patient light curves turn an engineering success into a lesson that improves the next mission. In truth, every deflection attempt is also a scientific expedition. We are not just moving a rock, we are learning what small worlds are made of, how they hold together, how they fail. That knowledge pays dividends even if, as is likely, we rarely need to fly such missions in anger. In the next part, I'd like to slow our pace and look closely at the target itself, at the geology of small worlds and the clues locked in Bennu-like rubble piles and iron monoliths. Because the way an asteroid is put together, from dust to boulder to buried void, decides how it greets our nudge, how its spin evolves, and how confident we can be that a millimeter per second, whisper spoken far away, will translate, months later, into a harmless, ordinary sky. If you want to know how to move a small world, you have to know what it is. That sounds obvious, but in asteroid country, the difference between a tidy monolith and a drifting heap of gravel is the difference between a clean push and a sigh of dust. When we arrived at the carbon-rich asteroid Bennu, we expected a firm, sandy regolith, something you could tap with a gloved fingertip and raise a polite puff. Instead, when the sampling arm pressed in, the surface behaved like a children's ball pit, swallowing the arm almost to the shoulder and flowing back like a slow liquid. It was a revelation. This is not a rock in the earthly sense. It is a cloud of stones held together by its whisper of gravity and a little electrostatic and van der Waals cohesion. You plan a nudge very differently for a world like that. Bennu is not only loose, it is lively. Early in the encounter, our cameras saw pebbles lifting off the surface and tracing fragile orbits before falling back like moths around a lantern. That means even small thermal or impact jolts can mobilize material in such weak gravity. The surface is a migrating skin where grains walk downhill, boulders creep, and occasional jets of pebbles escape outright. That behavior tells us two things of practical value. First, a kinetic impact will likely throw copious ejecta, amplifying the shove. Second, anything that depends on touching anchors, drills, harpoons must assume the ground may give way. And Bennu is not alone in its looseness. Japan's Hayabusa 2 mission returned samples from the dark asteroid Ryugu that turned out to be among the most pristine carbonaceous materials we've ever held, rich in water-bearing minerals and soluble organics of the sort, catalogued in the most primitive meteorites. This is deep time in powder form, a chemically gentle world where water altered rock in the earlier solar system, then the fragments reassembled into the low-density rubble pile we see today. For planetary defense, the chemistry matters less than the texture: high porosity, fragile clasts, and a tendency to rearrange under even modest shaking. Those traits whisper that a deflection by shove will couple as much to the dust you kick off as to the body you strike, and that is an opportunity if you understand it. The weak, boulder-strewn look of rubble piles has a family resemblance. Many of the small, rapidly spinning top-shaped asteroids, Bennu and Ryugu among them, where equatorial ridges like Saturn's rings glued down, a likely signature of long, slow spin-up under sunlight's tiny torques, a process we call the Yarkovsky-O'Keefe-Radzievsky-Paddock effect. Whatever sculpts the shape, the lesson is practical. Grains migrate, ridges grow, and interiors sort themselves under low-gravity tremors. That sorting is helped by what geophysicists nicknamed the Brazil nut effect. Shaking moves larger stones upward through a bed of smaller grains, slowly armoring the surface with blocks. In a world like that, every local patch can be different hard plate here, yielding drift there, and mission designers choose impact points with that patchwork in mind. We are beginning to read strength from shapes. After the deliberate shove at Dimorphos, teams pored over images of its boulders and found morphological hints of very low material strength rocks that fail like foamed cements rather than granite, faces that crumble rather than fracture cleanly. That matters because a soft, porous target turns a bullet strike into a spray of dust and gravel. The plume becomes your rocket exhaust, boosting momentum transfer beyond the bare mass of the impactor. It is one of the quiet beauties of the DART. Result: nature gives you a lever if you arrive with the right angle, speed, and expectations about what will break. Inside these bodies, mass is lumpy. Gravity inversions of Bennu, the art of inferring interior density from the way a spacecraft's path bends, suggest an underdense equator and center, as if mobile fill had migrated outward and upward over time. That is precisely the sort of hidden structure that changes how a nudge propagates. Hit near a void, and the shock may be muffled. Hit into a tightly packed lens, and it may couple crisply. The point is not to turn every asteroid into a medical patient. The point is to turn reconnaissance into numbers that bracket your momentum gain and your uncertainties. Some rubble piles are astonishingly long-lived. Dust motes, plucked from the surface of Itokawa, the tiny world visited by Japan's first Hayabusa, carry radiometric clocks that say the rubble reassembled more than 4 billion years ago and has survived the billiards of the inner solar system ever since. That longevity is not romantic, it is mechanical. A gravel heap can soak up collision energy and reaccumulate instead of shattering catastrophically. For us, it means that rubble pile is not a synonym for fragile. It is a synonym for forgiving in some ways, treacherous in others. And that nuance threads straight into deflection design. There are worlds at the other end of the spectrum, dense, metal-rich bodies that may be cousins of the iron meteorites in our museums. We have never up-close deflected such a target, but we will soon learn much more from a dedicated mission to a metal-rich main belt asteroid named Psyche. Metal is tough. Shock waves run differently. Ejecta behave differently. Gravity per kilogram can be higher. If a hazardous object one day proves to be iron-rich, you might favor a gravity tractor patient and indifferent to surface quirks, or design a kinetic strike that relies less on plume amplification and more on raw momentum. Either way, the reconnaissance pays for itself the moment you pick the method. Characterization is the quiet craft that underpins all of this. Thermal infrared telescopes in space tell us size and albedo, not just brightness, that turns a dot into a diameter. Radar from the big dishes sculpts shape models and spin states, and wonderfully often reveals that what looked like a point is really a peanut, a contact binary, or a moonlit pair. That last category matters. A non-trivial fraction of near-Earth asteroids are binaries, and you do not want to nudge a system without knowing which rock is doing the orbiting and how the pair shares momentum. The more faithfully we sketch mass, spin, partners, and porosity, the more calmly we can say, this much push, at this angle, on this day, and expect the sky to answer with the number we designed. If there is a poetic footnote in all this gravel and metal, it is water. On Bennu, bright, thread-like veins etched into boulders carry the spectral fingerprint of carbonate signatures of ancient water percolating through rock on a long-vanished parent world. Ryugu's particles are laced with hydrated minerals and soluble organics. None of this changes how you fly a deflection, but it changes how you feel about the target. These are not just hazards. They are archives. They are the debris of worlds that brewed water and carbon into minerals, then drifted for eons before wandering near our sunlit lanes. To move them safely is, in a small way, to curate the early solar system. So, when we say know your rock, we really mean know your rubble, your voids, your boulders, your spin, your partners, your past. Because a world that behaves like a ball pit wants a different handshake than a world of iron. In the next part, I want to turn that knowledge into a playbook, a short human casebook of targets, the yielding rubble pile, the compact iron, the peanut-shaped contact binary, the tight two-body dance, and walk through how the nudge, the tow, or the standoff would be tailored for each, so that a few millimeters per second in the deep quiet far from home becomes, months later, nothing more than an ordinary sky over our sleeping cities. Let me open the playbook and lay out a small casebook of worlds, because choosing how to move a wandering stone is really about choosing how to speak to its nature. I think it is fair to say there are 4 archetypes we should keep in mind: the yielding rubble pile, the compact metal, the peanut-shaped contact binary, and the tight two-body dance. Around those 4, there are a few unusual cousins: volatile, rich comets and fractured shards. But if we can plan well for these 4, we have a language for most of what the sky will send our way. First, the yielding rubble pile. Picture a low-density heap of boulders and gravel, held together by a whisper of gravity and a trace of cohesion. The surface may behave like a children's ball pit. The interior may hide voids and lenses of packed stone. Here, a kinetic nudge is not merely feasible, it is often favorable, because the plume of ejector can amplify the shove beyond the spacecraft's own momentum. The tactics become a choreography of care. We would map the spin, the mass, and the local slopes, then choose a sunlit patch that is smooth enough to reduce surprises but coarse enough to throw plenty of material. We would approach along a geometry that aims for downrange of the center of mass, where a small angular error does not squander the push, and we would carry a margin in case the surface swallows more energy than we hope. If lead time is generous, we might pair the impactor with a patient companion, a gravity tractor that arrives later to trim the result by gentle tow, turning a good miss into a very comfortable miss. In short, on a rubble pile, shove first, whisper later. Second, the compact metal. Imagine a dense, iron-rich monolith, a cousin of the iron meteorites in our museums. Metal is tough, it couples energy to shock differently, and when you strike it, it tends to throw less dust per unit of momentum. That means the ejector bonus is modest, and the business becomes one of clean arithmetic. If the warning is long, a gravity tractor shines here, precisely because it does not care whether the surface is slick as steel or studded with jagged plates. It never touches. If the warning is short, a kinetic impact can still work, but the design emphasizes raw closing speed, mass fraction, and a carefully chosen impact angle rather than relying on a generous plume. In the very short notice, very large mass corner of the decision tree, a standoff nuclear option remains in reserve, because ablation can deliver a decisive impulse to a stubborn target. Nobody reaches for that lightly. It sits behind diplomacy, law, and rehearsal. But it exists for a reason. Metal listens best when you speak clearly. Third, the peanut-shaped contact binary. 2 lobes kiss and share a tenuous neck. The gravity field is lumpy. The spin can be quirky. Here we are as interested in what not to do as in what to do. A badly placed shove could change the spin state, and stress the neck, or torque the body into a new attitude that complicates the next pass. The safer options are twofold. If time allows, a gravity tractor hovering near the most massive lobe can tow the composite gently without imparting an unwanted twist. If time does not allow, a kinetic impact can be designed to deliver as much linear impulse and as little torque as possible, aligned, as nearly as practical, with the object's instantaneous velocity vector, and placed on a patch whose local topography is well understood. The watchwords are impulse without spin and miss without mischief. Fourth, the tight two-body dance. Many near-Earth asteroids are binaries, a primary and a small moon in close orbit. The double asteroid redirection test taught us a powerful principle here. Sometimes the cleverest way to change a system's path is to modify the momentum of the secondary, which the pair will share through their mutual gravity. In a hazardous binary, the first question is which rock you intend to move barycenter or moon, and the second is whether changing the mutual orbit will introduce any unintended resonances during later flybys. The design sequence is methodical. Radar to lock down the masses and orbital period, light curves to watch for non-gravitational drifts, a nudge on the moon if momentum enhancement is desirable and the geometry favors it, or a patient tractor on the primary if torque control is paramount. In all cases, you check the keyholes, the narrow gravitational gates that could lead to future close passes, and you choose the sign and timing of the impulse to step elegantly around them. Around these four archetypes sit a few less common but important cases. A volatile-rich comet, for example, can surprise you. Outgassing jets act as their own small thrusters, altering the path as sunlight warms the surface. Long-period comets sometimes arrive with little warning and high speeds. If a hypothetical threat came from such a visitor, the menu tilts towards standoff options that do not require surface contact, paired with the best possible sequence of deep space tracking to refine the orbit quickly. It is a demanding case, which is why survey speed and sky coverage are so valuable. Days or weeks of extra notice can move the problem from improvised to engineered. Taken together, these cases suggest a simple decision tree you can say out loud. If the warning is long, prefer patient forces, gravity tractors, albedo modification to exploit the gentle Yarkovsky drift, even ion beam shepherd concepts that push by blowing a faint plume of ions just above the surface. If the warning is moderate, favor kinetic impactors sized with sober margins, and when possible, paired with follow-on craft to measure and trim. If the warning is short and the mass is large, keep the standoff ablation option on the table while diplomatic and legal frameworks do their work. At every branch, characterization is the hinge. Mass, spin, porosity, partners. Engineering likes redundancy, so the architecture often stacks options. A primary impactor carries a small companion that watches and radios home the plume geometry in real time. A trailing spacecraft arrives months later to verify the period change and, if designed as a tractor, to clean up the numbers. Telemetry and public communication are treated as mission-critical subsystems because reassurance is not a press release, it is a feed of data that turns anxiety into graphs. Even the philosophy of misdistance gets encoded. We do not simply aim to miss, we aim to miss by a margin that survives ordinary uncertainties, unhelpful talks, and small thermal drifts between now and the encounter. There is one last quiet discipline that belongs in the playbook: certification after the fact. When you have nudged a rock, you keep watching it not for days but for seasons and years, because planets are not billiard tables. Gravity fields are lumpy. Resonances are real. And a safe pass in one decade must not set up a narrower pass in the next. Verification is part of stewardship. And stewardship in the end is not only technical, In the next part, I want to step from the engineering bench to the council table law, diplomacy, responsibility. Who decides when to act? How do the United Nations frameworks, the long-standing treaties on space, and the habits of cooperation among observatories and space agencies become clear lines of authority and accountability when a small world is on our calendar? Because the sky writes the problems in dynamics, but we write the answers in trust. I think it's fair to say that when you move from engineering to governance, the vocabulary changes, but the stakes do not. A trajectory is a line on a plot. A decision is a line in history. So who decides when to act and under what authority? In practice, the answer begins with treaties older than many of the people who now write our flight software. The Outer Space Treaty, let me say the full name, the Treaty on Principles Governing the Activities of States in the Exploration and Use of Outer Space, sets the tone. It says space shall be used for peaceful purposes. It says nations bear international responsibility for the activities of their agencies and their private companies. It says you must avoid harmful interference, and if your plans might cause it, you should consult. In the calm language of diplomats, it is an ethic as much as a rule. Do not surprise the world. Beneath that sits the Liability Convention, which in essence says that if a space object launched by you causes damage on Earth, you are absolutely liable. Imagine what that means for a deflection. If you nudge a small world, and through some unhappy chain of physics and chance, debris falls on a third country, whose responsibility is that? The convention does not name asteroids. It names launching states. The implication is clear. Any mission that changes the path of a natural object must be wrapped in conscious consent, shared modeling, and transparent accounting of risk. It is not enough to mean well. You must carry the responsibility for consequences you did not intend. A third pillar is the Registration Convention. If you launch an impactor, a gravity tractor, or a reconnaissance craft, you register it. You say where it is, who operates it, and how it can be identified. That formality sounds dry. It is not. Registration is the opposite of secrecy. It is how you make sure that the first time a defense radar in another nation sees your vehicle, it is not a mystery. Planetary defense is a theater where trust is built with small, predictable, bureaucratic acts, and I say that with respect. There is a sharper legal edge that we should not glide past. A nuclear standoff option, an explosive device detonated at a distance from a hazardous object to ablate its surface, sits behind not only engineering caution, but treaty walls. The Limited Test Ban Treaty forbids nuclear explosions in outer space, and the Outer Space Treaty forbids placing nuclear weapons in orbit or stationing weapons of mass destruction in space. So if the world ever judged that such an option was the only timely way to avoid a catastrophe, it would not be a technical decision alone. It would demand a legal pathway, an explicit international mandate, probably through the United Nations, and a verification regime that convinces even skeptical states that the device will do exactly and only what is promised. That is as it should be. When you reach for the most powerful tools, you should feel the weight of law in your hand. Day to day, the choreography is more prosaic and more beautiful. Discoveries flow through the International Asteroid Warning Network, an open club of observatories, agencies, and universities that share astrometry, risk assessments, and public notices. When a case becomes serious enough to imagine a mission, the Space Mission Planning Advisory Group convenes engineers from multiple agencies to compare architectures and timelines. The point of both bodies is to prevent a scramble. If a future hazard appears, you do not want a chorus of uncoordinated offers and national press conferences. You want a single sheet of music with different nations playing different parts, all in time. Who then says go? Formally, a launching nation decides to launch, but legitimacy rides on company. You would expect a United Nations briefing, consultation through the Committee on the Peaceful Uses of Outer Space, and an agreed set of technical documents, the current orbit solution and uncertainties, the catalogue of keyholes to avoid in later decades, the proposed impulse, sign, and timing, the margins, the verification plan, the fallback plan. You would expect independent peer review of the consequence modeling. You would expect the operator to commit to open telemetry for navigation and to nightly public updates to the orbit solution so that any state can check the sums. In other words, you wrap the physics in process until trust is, if not inevitable, at least easier. There is an ethical layer I care about deeply: equity. The sky does not favor the wealthy. An impact point could sit anywhere on Earth, and the consequences could fall hardest on people who did not build the telescope, never mind the rocket. So planetary defense must be a commons. That means survey data released promptly and in formats useful to scientists in every time zone. It means capacity building training programs, internships, shared software, so that a student with a modest telescope under a dark southern sky can contribute astrometry as surely as a national observatory can. It means that tabletop exercises include ministries and emergency managers from regions that rarely appear in headlines but would feature prominently on a hazard map drawn by celestial mechanics. Transparency has its own psychology. False alarms erode trust. Missed alarms destroy it. The answer is not grand promises. It is calm, honest cadence. When probabilities change, say so. When an orbit, solution improves and risk declines as it usually does, with better data to celebrate that publicly. When a mission becomes unnecessary because the world turned out to be safer than we feared, do not mourn the effort. Pivot the spacecraft to science or rehearsal and say aloud that this is what success looks like. We bought time for understanding, and understanding retired the risk. There is also stewardship after the nudge. A deflection is not the end. You keep watching for years because gravity is subtle, resonances lurk. A safe pass in one decade can, through a chain of tiny pushes sunlight on a dark surface, a close pass by another planet, set up a narrower pass in the next. Part of any mandate to act should include a mandate to verify and to maintain. That is not theatrical, it is housekeeping. It turns a brave day into a quiet decade. If you like, you can think of the governance of planetary defense as an extension of something very human: informed consent. We consent together to act on the best available evidence. We consent to share the gains and the risks. We consent to be checked and to check one another. The sky presents the problem in dynamics. We present the answer in trust. In the next part, I want to step out of the council room and back under the night to the culture that makes all of this possible. The students counting stars, the amateurs timing occultations from back gardens, the teachers who turn a classroom ceiling into a map of moving lights, and the observatories that sweep the sky each clear evening. Because planetary defense is not only launches and law, it is a habit of attention, a civilization teaching itself to look up together, until looking up is ordinary and reassuring, and quietly, the reason an anxious headline never needs to be written. When I step out from the council room into the night, I'm always struck by how planetary defense really begins, quietly, locally, under ordinary skies. It begins with a child in a back garden, peering through a small telescope as a star blinks off for a heartbeat when a small world passes in front of it. That little wink is called an occultation. If you time it start-stop with care, and a dozen others do the same along a path across a continent, we can sketch the silhouette of an asteroid from nothing more than the choreography of starlight. I love that. It is modest, human, and powerful. A map drawn by patience rather than by force. Those sketches feed straight back into the larger machinery. Better shapes mean better orbits. Better orbits mean calmer decisions later on. The same spirit fills classrooms where teachers turn a ceiling into the sky. Paper constellations, hand-drawn ephemerides, a cardboard disc that shows how the planets stroll along the ecliptic through the seasons. These are not just lessons, they are habits of attention. If you teach a generation to look up and to keep notes, you are not merely creating astronomers, you are training guardians, people who understand in their bones that the heavens are dynamic and know how to be curious rather than afraid when a headline says a near-Earth object has been found. Then there are the meteor cameras, the silent watchers that ring the world on rooftops and school halls. Night after night they record faint streaks, triangulate the path of sand-grain visitors, and, a few times each year, point us to small meteorites sleeping in fields at dawn. Those little stones become pages from the early solar system. When a farmer stoops to pick one up and posts a photograph to a local museum, a chain begins. Laboratory analysis, classification, and sometimes an insight that changes how we think about rubble piles, water in rock, or the chemistry of organic molecules. None of that feels like planetary defense in the cinematic sense. Yet it is the foundation upon which the rare dramatic decisions rest. Understanding removes the pressure to improvise. Across oceans, survey. Observatories sweep the night like metronomes. They do not chase spectacle, they count. Each clear evening, the same fields, the same cadence, the same algorithms, searching for new points of light that move just a little against the tapestry of stars. When one appears, coordinates ripple outward, to students, to amateurs, to professional follow-up telescopes that measure the arc with finer and finer precision. In my more romantic moments, I think of those emails and circulars as the bloodstream of planetary care. The pulse is steady, the body is healthy. Culture matters because it shapes tone. Tone is the difference between drama and stewardship. A newspaper might be tempted by the language of doom. A community of observers prefers the language of likelihoods and updates. At the moment the probability is low, further observations are planned, we will report again on this date. You can almost feel the collective heart rate settle when a message reads like that. Calm is contagious when it is honest, and there is something beautifully egalitarian about this culture. You do not need a mountaintop to contribute. A rented hour on a small robotic telescope can capture a streak that closes an uncertainty ellipse. A handful of well-timed occultations across a country road can reveal whether an object is a single stone or a contact binary, two lobes kissing at a narrow neck, which, as we have already discussed, changes how you would nudge it. Even clouded out nights are part of the craft. Knowing when not to pretend is its own discipline. I am often asked why we should teach so much sky to children who may never write code for a spacecraft or sit at a radar console. My answer is that planetary defense is a story we tell about ourselves. It says we are capable of care at planetary scale and attention at human scale. A child who learns to measure, to check, to share notes with others in distant classrooms is learning the politics of trust without ever uttering the word politics. When years later, that same person hears that a small mission is launching to nudge a stone, they will instinctively ask the right questions. Who checked the sums? Who is watching the odds? How will we verify the result? How will we look after the communities under the projected path if an airburst remains on the table? That is citizenship in orbit. There is a quieter, almost meditative dividend to all this, and it is very much in keeping with the way I like to think about the cosmos. Looking up trains you to put events on the right timescale. Telescopes that scan the sky most nights of the year convince you that discovery is not a lottery, it is a practice. You begin to trust that even rare hazards are made ordinary by steady work. The language that follows is gentler. Not, we will save the world, but we will keep watch, we will measure, we will act early if required. That is the tone I wish for any future day when the risk dials nudge upward. a tone learnt in back gardens and school halls long before a minister stands at a lectern. We should also be frank about the side effects of attention. A culture that looks up regularly also notices other weather in the sky. We see satellites proliferate. We discuss how to keep orbits clean and radio quiet. We talk about light pollution and the way a dark sky belongs to everyone, not just to astronomers. Those conversations belong in the same family as planetary defense because they share a premise that the sky is a commons to be tended. When a town dims a few streetlights after midnight or shields them more thoughtfully, the reward is immediate: more stars and downstream, a better survey, a fainter streak captured, a tiny improvement in the odds that the next worrying object is found a little earlier. Perhaps the most heartening thing I have learned from years of talking about this is that people want to help. Invite a community to a meteorite search. They will arrive with thermos, flasks and high spirits. Invite schools to time an occultation. They will build cardboard chronometers and practice with the moon. Invite a local paper to publish the How to Read a Risk Notice checklist. They will run it on page 1 when a story breaks, and the comments will be calmer than you feared. None of that requires a launch vehicle. It requires an invitation. So, let me gather the threads. Planetary defense lives in 3 intertwined places. The bench, where engineers size nudges with the poetry of numbers. The council table, where diplomats wrap physics in process and consent. And the night, where ordinary people make extraordinary measurements, and simply by paying attention, turn the rare into the manageable. When those 3 places talk to one another often and plainly, the rest follows. The toolkit works, the tone holds, the public stays with us, and the sky remains, as it should be, vast, beautiful, and reassuring. In the next part, I'd like to return to the original question with a clear human arc. What if an asteroid really were on course to strike? Not as headlines, but as lived days. We will walk through 3 calmly imagined scenarios. A small stony visitor that fails aloft over land, a mid-sized object that reaches the sea near a continental shelf, and a larger, rarer body that demands a launch nudge. And we will let the physics, the planning, and the culture we have just explored write the timetables, the public messages, and the small, practical acts that make all the difference when the calendar turns toward an appointment with a wandering stone. Let's walk the lived days. First, the most likely scenario. A small stony visitor, the size of a room, on a shallow path, fails in the air above a town. In the weeks before, astronomers have watched the dot, refined the orbit, and told local authorities that an aerial detonation, not a crater, was the dominant risk. On the morning of the event, the public messages are simple and kind. Stay indoors. Move away from windows. Draw curtains. Do not stand with your phone filming a bright sky. When the object breaks, the blast wave arrives, tens of seconds after the light. Glass is the villain. Lacerations are the common injuries. A few concussive injuries occur where people meet falling ceilings or doors. We learned this cadence not from imagination, but from the Chelyabinsk airburst in southern Russia. Thousands treated, overwhelmingly for cuts from shattered windows, and a trove of field measurements showing how the shock propagated and where glass failed. The lesson is strangely humane. Physics says step back from glass, and that is enough to turn a frightening morning into a repair bill rather than a tragedy. If you were there, what would it feel like? First the streak, bright as a rising sun. Then a silence you can mistake for safety. That silence is only distance. The pressure wave is coming. Indoors, you keep to interior corridors, close doors, and wait for 2 waves. The first strong pulse, then the rattle of reflections. Outside, you kneel behind something solid and keep your face down. Emergency services pre-position ambulances for glass injuries, not burns. Hospitals stage gauze, sutures and eye wash. Engineers inspect critical infrastructure afterwards. The numbers, you never see the estimated altitude of breakup. The yield of the airburst come from models that have been quietly validated for decades, like the Earth Impact Effects framework used by researchers and planners to translate a body's size, speed, and angle into damage footprints. It is not theatrical. It is logistics guided by equations. Second, a mid-sized object, hundreds of meters across, arrives over water near a continental shelf. Popular culture likes to imagine an ocean-spanning tsunami, but the ocean does not give up its energy so readily. In the last decade, a focused workshop brought together impact modelers and tsunami experts from space and ocean agencies. Their shared conclusion was reassuring and precise. For the sizes we are most likely to face in our century, the efficient hazards are near-field coastal surges and severe inundation in bays and harbors, while far-field, basin-wide tsunamis are unlikely from such impacts or airbursts. Over deep water, much of the energy goes into a transient cavity and short waves that decay with distance. Over shelves and in confined geometries, those same energies can translate into dangerous local run-up. That is sobering for ports, but it is not the end of the world. It is a map for planning. What do coastal authorities do with that map? They borrow from earthquake tsunami playbooks, but they tune the choreography to the space-driven updates rolling in. Evacuation is lateral and upward. Move to higher ground outside projected surge zones rather than fleeing long distances along clogged roads. Keep harbors clear of first responders until the water has settled. Stage rescue boats in sheltered inlets rather than on open piers. Because the impact timing is known to within minutes, and the footprint tightens with each radar pass and light curve, alerts can be tiered: a pre-alert the day before, a firm warning hours before, and, if the object fragments aloft, a rapid all clear. That timing discipline is not hypothetical. It is exactly the cadence exercised in recent national-level tabletop drills that rehearse the handoff between astronomers, emergency managers, and foreign ministries. Third, the rarer day. A large, well-characterized body with a non-trivial impact probability years ahead. The sort of case that justifies a launched nudge. Here the comfort comes from lead time and from institutional memory. The current planetary defense strategy, refreshed in the early 2020s, sets out, soberly, that civilization-level threats are associated with kilometer-scale bodies, most of which are catalogued and none of which threatens on relevant timescales, while the city-to-region tier, around 140 meters, remains the priority for discovery and tracking. It also specifies the muscles we exercise: improved survey eyes, better modeling and information integration, and decision frameworks that connect observatories to civil protection and space agencies. So when the calendar says mission, the playbook is not improvised. It is already on the shelf. The lived calendar of such a mission is oddly calm. Months of orbit refinement shrink the uncertainty ellipse and size the required millimeters per second change in the asteroid's velocity. Agencies agree a design, often a kinetic impactor, possibly paired with a slow push tractor, and set a last responsible launch date that still leaves time for the nudge to accumulate into a safe miss. Public messages stay plain and regular. The probability today, the next observation window, the margins we carry, what we will learn even if the risk declines. That last point matters. The 2024 exercise made it explicit: transparency and cadence. Lower public anxiety and make it easier to stand down gracefully if improved data retire the hazard. A cancellation is not a failure. It is the system doing exactly what it was built to do: buy time for certainty. At the moment of action, the choreography is almost workmanlike. The spacecraft departs in an ordinary launch, coasts, and trims its path with small burns. Telescopes keep watch, feeding nightly updates to the risk tables. As arrival nears, autonomy takes over. Light takes minutes to cross the gulf, so the vehicle must recognize a mottled, tumbling world and thread itself to a sunlit patch at just the right angle to maximize momentum transfer without adding needless spin. If the body is a gravel heap, the plume will likely gift us a momentum bonus. If it is metal-rich, we rely more on raw mass and speed. After contact, nothing may look dramatic. The proof is written in a changed orbital period and, later, in independent verification, that no new gravitational keyholes have been set up for future decades. Even this housekeeping step, watching for years after a nudge, is part of the plan. Strategy documents require it. Stewardship demands it. Across all three scenarios, two quiet ideas do most of the work. First, time turns danger into navigation. A change of a few millimeters per second, delivered far away, becomes a miss by a comfortable astronomical distance at Earth, an outcome you can design, simulate, and verify with tools that have been tested for years. Second, language is a tool. Clear, tiered messages: what is known today, what will be known next, what to do if you are near windows or near water, turn a headline into housekeeping. The best day in planetary defense is not heroic. It is ordinary because thousands of people have practiced making it ordinary. In the next part, I want to gather the myths. We have quietly walked past myths about global tsunamis, about last-second nuclear heroics, about unknown rocks from nowhere, and replace them with the simple, accurate pictures we actually use, from how detection really works to why you so often see probabilities start small, wobble, and then quietly fall to zero. Because understanding is the softest kind of protection, and it is the thread that ties the science, the planning, and our shared, very human calm. I think it is fair to say that what began as a question, what if a wandering stone should one day share our path, has become something gentler, a reminder of who we are when we look up together. We have walked through the physics, the tools, the laws, and the culture, and none of it asks us for heroics at the last minute. It asks for attention. It asks for the long kindness of preparation. The sky is not a theatre of dread. It is a great, slow clock, and we have learned to read the hands. When I picture the end of this story, I do not see a countdown. I see an evening long after the headlines are gone, when a small spacecraft, now cold and quiet, is drifting under a pale star, its work already folded into the numbers we keep. Somewhere on Earth, a teacher is pointing at a wall where the constellations have been drawn in chalk. Somewhere else, a child pauses in a back garden because a bright point is moving against the stillness, and for the first time understands that stillness is an illusion, that everything is in motion and always has been. The child will not be afraid. The child will know that there are people keeping watch. That is the image I carry, not drama, but stewardship. Telescopes sweeping the same bands of sky, night after night, like careful gardeners. Engineers building small, immaculate machines that do exactly what they were asked to do, then yield the stage to measurement. Diplomats writing down, with patient clarity, how we will decide and how we will share the responsibility for deciding. Volunteers setting up meteor cameras on school roofs. Amateur observers timing a star's gentle blink to trace the outline of a stone no one will ever see with their eyes. None of them alone can deflect a world. All of them, together, make deflection unnecessary most of the time and calmly sufficient when it is required. There is a humility in that picture that I find deeply reassuring. We are not the center of the universe. We are a species on a blue world, warmed by a star, wandering through a field of ancient debris. The debris is not malicious. It is the leftover poetry of planet making. Some pieces glow softly in the infrared like embers under ash. Some carry water locked in minerals, or carbon chains that remember chemistry older than Earth. We map them because it is sensible. We move them, when we must, with the lightest touch we can devise. We learn from them because every handful of dust and every sculpted boulder is a page from our own beginning. If you step outside now, whatever the hour is where you are, and look up, you will most likely see nothing out of the ordinary. That is the point. The ordinary is the victory. The ordinary is millions of measurements, tidying risk into fractions and then into nothing at all. The ordinary is a quiet network of observatories and agencies and classrooms where the habit of attention beats like a slow pulse. The ordinary is a policy document with unglamorous verbs: coordinate, notify, verify, that turns celestial mechanics into timetables and clear instructions for mayors and harbour masters. The ordinary sustains the extraordinary. I often think of time as the soft power of the cosmos. Given time, a small whisper at the edge of space becomes, months later, a miss by a comfortable astronomical distance. Given time, language that might have been alarming settles into updates and rehearsals, and finally into gratitude that nothing very interesting will happen on the appointed day. Given time, a child with a cardboard planisphere becomes the engineer who writes the line of code that holds a tiny spacecraft steady while it aims itself at a sunlit patch on a mottled stone. Time is the currency we buy with eyes and patience, and we spend it on calm. So let us end with gratitude. Gratitude for the people who sweep the sky while most of us are making dinner. Gratitude for the ones who can turn equations into instructions and instructions into aluminium and sensors and a small burn at the right moment. Gratitude for the international habit of sharing both the arithmetic and the credit. Gratitude, too, for the stones themselves, for the honesty of their orbits, for the stories they carry from the first warm days of the solar system, for the way they remind us that our history is part of a much larger history that moves at once more slowly and more surely than we do. And let us end with perspective. The Earth has circled the sun more times than we can comfortably say aloud. Life has endured ice and fire, flood and famine, the steady ticking of deep time. We have learned to hear the universe in gravity's low notes and to see it in wavelengths our eyes cannot perceive. We have flown cameras to the edges of comets and tasted the dust of asteroids and returned it in capsules that came home on pillars of flame. All of that is the preface to a simple, practical kindness. If a small world should wander too near, we can persuade it, politely, to take another path. So breathe. The night is vast. The stars are where you left them. If you listen closely, you can almost hear the quiet work continuing, the murmur of servers storing another clear evening's images, the low conversation of engineers in a control room, the click of a backyard mount tracking a slow, precise arc. Somewhere, a message will go out later this week. The probability has fallen. Further observations will follow. We will report again on this date. That is the music of reassurance. And when the lights go out and the house settles, know this: the sky above you is not indifferent. It is simply grand and slow. And we are now a species that has learned its tempo. We keep time with it. We keep watch. And in that shared, patient attention, across languages, across oceans, across the years, there is a kind of quiet promise that is both scientific and human, that the world will go on turning under ordinary skies, and that tomorrow will arrive, as it most often does, with the sound of birds and the first pale light easing across the horizon.